Here comes one more. All right, so like I said, we are going to go through 2 chapters today. They're really pretty easy to pair together. They have some new ideas in them, but the new ideas are still so steeped in old things we've done. I don't feel like it's too crazy new for you. I'm not too worried about overwhelming you today. So what we're going to do today is we are going to introduce differential equations. And by the way, I will add, for those of you who are in the building, you are welcome to unmute yourself, but I will say because of the way the mics work, hopefully only one of you would unmute at a time, just so we don't get too much feedback. All right, and for the 3 of you that just got here, go ahead and turn your cameras on. We're just starting. We are about to do something with derivatives that we have never done before. We're going to put them right into the equation. All right, I've got one recommendation in the chat. Ultimately, as you look at this problem, we're going to be thinking about what are some situations where your second derivative is equal to your function. We have something cyclic. So in the chat, I've gotten the recommendation. E to the x. What are some other things that would work? Well, let's throw some stuff at you. Yeah, you technically could have a function where your y just equaled 0. That would work, because then you'd have 0 minus 0. If y equals 0, and again, we're looking for y equals, not anything else. Natural log is a good guess. We can give it a try. I know one that I was expecting to hear from you is something like sine, because we are taking a second derivative, so we're going to see if it comes back. And I'm not saying that these work, but let's give them a try and see if they do. So, if we take y equals e to the x, what is the first derivative of e to the x? There we go, Cormac. And what's the second derivative of e to the x? All right, just hearing from Cormac. Everybody else awake today? Keaton says no. All right, so we get e to the x out a couple times here. So, since we can see that these are the same, we can see that the second derivative minus the original function does equal to 0. So, this is a possible solution. Now, this is a case that we definitely wouldn't use typically, but if your function did equal 0 to begin with, then its derivative also would equal 0, and its second derivative would also equal 0. So this, we could say, is a possible solution. Although an improbable one, since there's not really a function there to play with. I mean, it's still technically a function, but there's kind of an absence there too. And let's see, if y equals the natural log of x, are these two things the same? So is it going to be a possible solution? Andrew tells me no in the chat. All right, and let's go ahead and try that y equals sine of x. Yep, Sathya, that's fine. Oh, Cormac, that's fine too. So, are these the same? Andrew Woods told me in the chat. You can also tell me with your faces. Melina's telling me in the chat. Keaton's telling me in the chat. JC and Hunter are telling me with their faces. They're very, very similar, but just that little bit of a negative negates our problem, because this is saying that the sine of x minus the negative sine of x equals 0 when I look at the second derivative minus the original function. And this is not true. I mean, it's true for specific x's, but we need it to be true all the time. So we would say that this is also not a possible solution. And I do want to do one more that's a little bit more, but only slightly more adventurous than what we tried before, because we're putting some coefficients in here. So let's give this a try. If you're going to take the derivative of 4 to the times e to the negative x, remember it's going to be 4 times. With any exponential function, you just get it back again. And then you need to take the derivative of what's upstairs. So the derivative of negative x becomes negative 1. So in other words, I end up with negative 4 times e to the negative x. And then my coefficient stays alone. I'm going to take the derivative of e to the negative x, which is going to be itself back again, times the derivative of negative 1. And those negatives will cancel. Was this a possible solution? Heard from Andrew Woods. See some head bobbers. Heard from Hunter. Heard from Keaton. And from Annie and Nelina. So, when we're talking about differential functions, differential equations, you could have a situation where you're going to have many different equations that could fulfill the requirements of the equation. Cormac, yes, really, it could be anything. He has could it be anything with e to the negative x? It could be for this case. But of course, when we change the differential equation, then it wouldn't necessarily work. So for example, if my equation had been y to the fourth, and remember, we never really seem to take fourth derivatives, but this is how you would write it. Had it been this, then y equals sine of x would work, as well as anything that was in e to the x. Of course, if I put a number up there with the x, that would no longer work anymore, because when we take the derivative, that would get pulled down. I'll pause there to let you catch up to me. And while you're doing that, I'll go through the roll one more time, because some of you have shown up. And again, for those of you that showed up late, I'm not counting tardies today, because it is just kind of a crazy day for everybody. Nalina, yes, that is c times x to the third power, where c is just a constant. And Annie, that's what that is. Kind of does look a little bit like an L, or I could see where you could say it was an L. Alright, so start playing with this one. I have faith in you. You know what your y is. I believe in you and your ability to take its derivative. Once you've taken the derivative, plug the original function and the derivative back into the equation and tell me if it works. Cormac, that's close. You gotta remember your C value there. What's funny is for a lot of you, not only is it your face I've gotten to know, but it's your background. And putting some of you in a new background, I'm getting thrown off. Like, wait, where's this person? Are they? I know they're here, but where are they on the screen? Just because I can't pick you out as quickly with your background.
Yes. No. We are not paying for it.
Alright, so let's give this a try. If I'm going to take the derivative, then I'm going to bring that 3 down and subtract 1 from the power. And then in my function, I've got x times 3c times x squared minus 3 times c x cubed equals 0. And we want to check and see if it does. And so if I simplify this out, I've got 3cx cubed and 3cx cubed. So I can see that it does equal 0. So this would be a solution. So cx to the third is a solution of x, not x squared, x times the derivative of y minus 3y equals 0. So it's kind of like Cormac earlier had said something about, I'm going to scroll up here for a second. I promise I'll bring the screen back. But when we did this right here, in the chat he asked, wouldn't any number times e to the negative x work? And I said, yeah, it will. And the whole idea with differential equations is a lot of times we're going to just say, you know what? Any constant here will work. We can fill that in later based on what the situation is. So this is a general form, but the question also asks us to find the particular solution, which means we want to be specific, which means we want to know what C equals. We want to give it a number. So it's very, very easy to handle that, because now that we know that this works, we know that we can plug in what our y equals and what our x equals and use that to find the particular C that we want for this situation. And I know I'm crowding my screen, which is why I'm using different colors. You organize it however makes sense to you for your particular piece of paper. But that's what we would call a particular solution. When we find the exact equation we want, the equation's the solution. Normally when we talk about solutions, we're talking about numbers. But here it's an equation that we're looking for. And I still see some people are copying, so I'm just pausing so I don't rush you too much. So we are picking up the pace, I will say, a little bit. There are 3 potential test days for the AP test, which normally doesn't happen. It's only because of the COVID situation that they're doing that this year. And so I'm still trying to hear back from the office. I've contacted them a couple times to find out which test date we're giving you. And if it is the earliest test date, how many classes do you think we have left before the test? Show me with your fingers. Give you a hint, it's less than 10. Keaton, you're close. Nalina, you've got it. JC, you've got it if you're counting today. If you count today, there are 8. After today, there are 7. And we still have a chapter and a half to go through. And review. So I'm really hoping we give you the end of the time. Because honestly, too, it's just for us when we get out of school a little later. It's nicer to have the end of the year. I should say end of May. So I'm hoping that's the one we have. But I'm still waiting on Mr. Katoa. So the last test day is actually in June after school lets out. And I'm assuming the school signed you up all as a group. Normally this test would be the first week of May regardless. Because there are a lot of schools that get out in early May in the country. Like the high school I went to, we were out by May 12th. But we started every year by like August 7th, so we just started earlier, got out earlier. And for you guys, it's either going to be May 4th, May 24th, or June 10th. I can't remember the dates off the top of my head, but it's something like that. So either way, I'm going to be combining a few chapters. And this one was a pretty easy one to do. And I think I do not see anybody writing anymore. So let's go on to this idea of slope fields. Yeah, that's what I'm saying, Nalina, is the last test date for AP is after school lets out. That one, though, has an at-home, or it's a potential to take it at home. So the first 2 test days are in the building. You have to go to the building to take them. That 3rd test day you can do in the building or at home. And so that's where I think the school has to work that out. That part's above my pay grade. So this is the example we're going to do. But first of all, I'm going to cover up the screen for a moment. We'll come back to it. In your textbooks, have you seen things that look kind of like this? There's actually a section I skipped over that had slope fields that introduced them. And I thought, you know what, like these are easy enough to do. I'm just going to wait until this lesson to get to them. So the ones that are in your textbook don't have quite this many lines. And there's no color coding to it at all. Claire, I see your message in the chat. Thanks for letting me know. So with a slope field, it's all the possible solutions rolled up into one. So like in that last problem, we found a particular solution, which was a very exact equation. I can graph that equation and get a very specific line. What happens with a slope field is it's going to show me where my function would go, and I just kind of make my reasonable estimates off of that. But let me pick a good color here. And a thicker line. But you're going to think about this as wind patterns. If you put an object, say, right here, I can see I expect that it's going to go in this direction. And of course there wouldn't be an actual arrow on it. It would just be a line. But I can see that if I put the object here, oops, it's going to go in this direction. If I move it over slightly, I can see it's going to curve this way. If I put it right here, it's going to curve something like this. And a slope field is just a way to show all the possible solutions at the same time without overwhelming our senses and having lines on top of each other. Each of these points is just representing a slope. It hurts your brain to look at. Well, just wait. This is definitely going to be on the AP test. Slope fields, they're not like the biggest deal, but they 100% will show up. So what happens here is, well, let's just remind ourselves, first derivatives are the same things as slope. So when you're talking slope fields, we are going to be talking about first derivative equations, not differential equations with second derivatives like we did just a moment ago. And remember, x and y are coordinates. So in other words, this is saying your slope at a point depends on the point's coordinates, which should make sense because the y value depends on the x value you plug in. In this case, it's the slope depends on both the y and the x. So, for example, we're going to use this equation here. And we're not going to do nearly as many lines as we saw before. Let's just do a few basic points. Actually, you know what? I'm going to scroll this down here. I'm going to remind myself of the equation. I'm just going to make this bigger because I got a lot I'm going to put in here. So in your notes, give yourself some space for what we're about to do.
It was a full battery replacement, and the battery itself cost $199, and the work was $50, so it came out to $249.
And so I'm marking these coordinates pretty heavy, more heavy than normally I wouldn't mark the coordinates, honestly, on a problem like this.
I heard back from Shalina. She had talked to
Just depends.
Dennis about it. Dennis needs to go to her office and check
And
out
then let's see, the differential equation
to pay for it.
is given here.
Okay.
And then at that point,
So the reason I'm making this super big is I'm going to put more information in here than we'd ever put into slope fields, just to get you used to them. First thing I'm going to put down is we have all of these coordinates. So for example, this was the point 0, 0. This is the point 0, 1. This is the point 0, negative 1.
When they called, they said that he had us down, and so he just wanted us to get the card from Shalina,
no,
go pay for it, and leave it in his office.
he will need to do that. I'll send him an email and just let him know that he needs to do that
Yeah, that's what I was thinking, but
because he will need to reconcile the charges with Shalina to his 20 account.
awesome.
Yeah.
Alright. Yeah, thank you, Dan. So,
Okay.
And all I'm going to do to find the slope is to plug my coordinates into the equation. So, and again, I'm going to put more detail into this than we normally would write, and we'll redo the slope field without all this extra information. I'll pause for you to catch up to me. Nalina, to respond to what you said in the chat, I mean, maybe I'm wrong, but I was just looking at the AP site this week, and it was only the third test that it said could be online. Or that could be administered at home, I should say. Maybe there is a way to do it online from the school. I don't know. But hopefully they'll do multiple test days in the future if you take any AP tests after this year, for those of you that are juniors and lower. Just because they have the date set for schools like where I went to high school that get out weeks before we do. So you guys actually, here in Utah, have weeks less to study the material before the test comes up. Now, what you're going to do is on each of these dots, on each of these coordinates, you're going to draw in a line that has roughly the slope that you're looking for. For example, if your slope is 0, that means you have a horizontal line. When your slope is 1, that's a perfect 45-degree angle. If your slope is -1, that's a perfect 45-degree angle, but going down. And then, of course, if it's 2, it's just a little bit steeper. So down below here, this is what you would expect to see for the slope field of our equation, because it wouldn't have the coordinates and the equations written out for each point. It would just be these lines with the slopes. Technically, Cormac, they would still be defined. They just wouldn't be defined in terms of a function. And it really, let me see, he asked if the ones that are going straight down would be undefined. I'm just going to cover it up for a second. I'm going to pull it off the screen. Because there are several that look like they're going straight down here, but... Oh, I guess I didn't pull it off the screen as much as I thought. But yeah, I'm going to go ahead and cover it up. So you're still dealing with the whole idea of rise over run. Everything that is on this problem does have some slope to it. There's none that are undefined. But you will have the possibility of having things that will go straight up and down. So they will be undefined in the sense that it's a vertical line occasionally. Depending on what the equation looks like, though. But it is possible here. Which is one reason why I'm being very careful to call them differential equations and not differential functions. Because they will sometimes violate the function rules. So what do you think of these? Okay. Let me verify how much I have left. Well, we might have time at least to start it. This is one reason why I want everybody on a computer. I didn't necessarily make this look pretty because I thought if we were running too far behind, I was going to put this into your homework. But I want you to go... Oh, apparently I didn't save this. To Canvas, and I want you to go to Modules, and I want you to go to the lesson 30.1 on your Canvas page.
Yes.
So go right here.
We just got a call from the underground lab. They said that the internet is out. Do you think that could be OIT?
Which underground lab?
U-232?
Isn't that underground acoustic or underwater acoustics?
And I have these two items here for you. Let's go to the second one first, just to show you. This is for your own information. Somebody has put together using a lot of individual equations for each individual line. So thank them for putting all this work in, because that's several hundred lines right there. But they've put it in so you can create your own slope field generator. So for example, the one we just did was x minus y. And there we can get an idea of what this equation, we're here. They are going to use g of x of y is going to be the same thing as my derivative. Because Desmos doesn't have a good way to just put a derivative in right there. But we can see a more complete slope field. All we graphed just a moment ago
You might need to go and check and
was this portion right here.
the network cable that they're connected to. Making sure it's plugged in.
And we could have gotten a lot more points, but it would have just taken us more time to do that many. So I put this into your lesson page so that you could use it to check your own slope fields. You are going to have a couple slope fields you're going to put together in your homework. Please do at least some of it by hand because the AP test you're going to have to. So make sure you know how to do it. But then you are welcome to use this calculator to create the slope fields that you would like. So for example,
Some faculty or some research areas have just bought their own.
you can change this equation to anything you want. So I'm going to pull up a problem from the book. Here's one that's from inside the lesson pages. There we could do 2x plus y and see what that slope field looks like. See what other sort of interesting things they have. We could do tangent of x divided by y. You can put anything you want, just whatever the slope field wants. And you're going to, again, the whole idea of slope fields is they give you all the general solutions. And with the general solutions, treat it like if you put in a point, think about how the wind would carry it. All right. So that is there for your use, but I'm not going to spend time on it except for just to point it out to you. I gave it to you. So if you want to have a way to calculate these with technology, there it is for you. But what I want to do, and I'm not going to spend necessarily enough time to finish this, I want you to click on the first link, the student activity. I'm going to give you about 8 minutes to run through the student activity. And it's just practice on your own with slope fields. So please do put your real name in. I'll give you a couple points for doing this. And it's just, I think it was 7 slides. Nope, 6 slides. I want you to read through the scenario. Some of them you're going to draw on the picture. Some of them you're going to have a little chat box to write in. Go ahead and take 10 minutes to do these 6 slides. And then we'll reconvene. And then I'm going to pull up where I can see your progress on this other screen.
in that room. And they
And
are
if you finish before 10 minutes, then we'll move on.
good from what I'm seeing.
Oh, so those would be completely managed by OIT, not even through our switch?
Yeah.
Okay. Well, I'll see if maybe it's just something is unplugged or something.
Yeah. Physically check it. You might want to take a laptop with you or the ether scope.
Okay, and there are 19 of us in class, and there are 15 so far in the activity.
Sounds good. Thank you, Dan.
You're welcome.
Okay, there are still 2 of you that aren't logged in yet. So, number 2 is asking you that they gave you a point right here, and they want you to use what you see with all these slopes to, if you were to move to the right, where would you draw this line so it just kind of follows the breeze? And so draw something that makes sense. So for example, this would not make sense because you're not going with the breeze. And I will say on number 2, I see a lot of partial lines on number 2. Number 2, the answer is not a function. In other words, the shape you draw on the screen should violate the vertical line test. Cormac, very, very good question. He asked, what is DE? DE is differential equation. People get tired of writing it out all the time, so you'll either hear it simplified as DE, or where I went to college, we called it a Diffie Q, for differential equation. And it's our differential equations that give us slope fields. Anything that has a derivative in it technically is a differential equation, including everything we've studied earlier this year. But we're adding to the complexity of how we could use those derivatives in equations. Okay, about 2 more minutes. I can see most of you right now are on problem number 3. I do have one person who's almost done. Nobody's on number 6 yet, but I have a few of you that are close. Had a few of you on number 5. I'll extend this by just a minute or two, but do try to go as fast as you can, because we're definitely not done yet. And Trisha, are you still there? Okay. Trisha, that's all right. Sometimes technology needs to catch up. Okay, 2 more minutes, then we're going to move on.
And then I just got back from U-232.
Yes?
And yeah, it looks like those two ports are not working.
Do you have access to Slack? Or
I don't know. I know Shane does though. I could have him send a message.
you should be added to Slack or be able to sign into the OIP Slack.
Yeah, I just haven't downloaded it yet. I can do that real quick.
Okay. And the port numbers were correct down there, or did you have the port numbers written down?
I didn't have them written down.
You said you did not?
No, I didn't.
Yeah, we will need those port numbers.
Okay. Do you remember that network tunnel we saw before?
I do. Were the ports that are connected to on when you walk into the room on the right wall? Or the wall to the right?
When you walk into 232, there was two ports from OIT in the middle of the ceiling, kind of on the left.
All right, go ahead and
And then there was
minimize your screen.
which
Take it back to my screen.
check, which had the
Now I've got this set up so that the program gave each of you a mathematician's name. So even you can't tell who you are. I can tell you I'm Diana Davis. But just to show you just kind of some of your solutions, my favorite was Herman Wiles here, and you know who you are with the smiley face. But we see a pretty good circle over our system on this differential equation.
Well, once we have those port numbers, we can put it in.
We see a pretty good parabola system with this equation.
in the network center one.
On this one, it was interesting to me because depending on where you put your point, it made potentially a bigger difference as to what your slope field would look like.
Okay. I'll go
So when I overlay your answers, there was a lot more chaos to this one. Now, I don't agree with all of these lines personally, because you do want to make sure that your line tends to follow the slopes that you see. Like right here, this one right here kind of goes through the points. It doesn't follow the slope, the wind pattern, we'll say. And then creating your own. So Evelyn Granville here has, it looks like you were doing what we did before, which makes sense, drawing in the line here. This one was looking for a slope field, and we can see we have some different answers here. Like right here, we have some flat and some that is slope. We obviously couldn't have that. We need them all to be in the same, so you would want to check your math. But play with this activity. This activity is a great one to get you used to what these slope fields are in a way that's not overwhelming, because personally, if you had to draw in every single one of these slopes yourself by hand, that would take forever. So to use the technology, if you have to do more than, say, like 10 slope lines, just use the technology to help you through that. All right. So we've gone through what slope fields are. We've gone through the visualization of the differential equations. We've gone through verifying the solution, just seeing if it works. But what we haven't done yet is actually solving differential equations. And that's how we're going to finish out the class, including a word problem. But the word problem is not going to come yet. So with our differential equations, we are starting out pretty simplistic because we are using first derivatives. Obviously, the more derivatives there are to the situation, the more work it will be to solve the problem, to find general or particular solutions. And we are going to look for the general solutions, which means we're definitely going to have C's involved in our answers. Some constants that we do not know. So the first thing I would do on a problem like this, personally, this is just me, I would change the way you write the derivative. So, oh goodness, that scared me. One of you, I don't know who, unmuted just for a second and I jumped. All right. La, are you still there? There you are. I am recording this. You're missing kind of the heftier part of the lesson. But at the same time, yeah, you're going to have to go to the recording to get this last bit. Which, by the way, before you go, on my records, I have several of you told the school that you were going to be doing school in person, and then I see that you're online at home. I am not going to follow the school's directive, but your other teachers might. I want you to know that the directive of the school was if you attended school in a different way than you said you were going to, that we're supposed to mark you absent. So I'm not saying take advantage of me and say, oh, I feel like sleeping in, so I'm going to work from home today. But I'm saying whatever you told the school you're going to do, the school is expecting you to commit to that for the rest of the year. So whatever you said you were going to do, please do that. This is a class that, yeah, Annie, that's fine. That's good to know too. Yeah, because Mr. Wilson had told us to mark you absent if you were online but said you were going to be in the building. And then they weren't necessarily going to let you in the building if you said that you were going to be online. So just, yeah, for yourself, make sure you do what the school committed to and try to avoid missing my class as much as possible because the AP test is coming and we're full steam ahead. But yeah, Lala, you go do what you need to do, and Claire, I know you're going to have to leave in a minute too. It is what it is. Satya, when you say your only class, it's just, I'm assuming you mean on B days, or if it's your only class total, it's just whatever you told the school. I've got over here, let's see, we'll hide your student ID numbers. But I have over here what you said you were going to be doing. In person versus online. And I did make a note of, some of you hadn't specified when I got this list, so that's what some of these are. But then some of you, I saw that you said you'd be in person and you were online today. I did make a note of that just so I could see it, but I'm not going to report it to the school. But I do want to let you know because your other teachers will. All right, anyway, back to the differential. What's great about setting it up in its differential form is we can play with it with some algebra and get it set up for an integral. So right now, for example, if we have dy over dx equals 2x over y, while some mathematicians will frown on this, you really can treat these differentials like they're fractions and move them to the other side. And while we're at it, let's go ahead and two birds, one stone. take care of that as well. So that we get y dy equals 2x dx. Oops, sorry. So you want to rearrange it so your y stuff is on one side and your x stuff is on the other side. And once you have that, you're going to then integrate. It's a legal move so long as you do it on both sides. And then you're going to follow through on your rules of integration. And you do need to put a plus c, but you don't need to put a plus c on both sides because we just consolidate them on one side. I personally prefer to put them on the x side. Because plus c on both sides just still would add up. You could move the c to the other side and still have just plus a constant. And legally, you could leave it like this, but there is a more standard form for the equation. For example, while you can leave like this, mathematically, we have formats that we just prefer to see. So in this format, we would prefer to have your x's and y's on the same side.
They should be connected. Well,
And we'd prefer to be able to get rid of the fractions.
IP phone one goes to an access point.
Those two go. One of them goes to nothing. One of them goes to the computer in there. And then it looks like there's two more ports which are
And so we would prefer to see the answer like that.
cabinets. So I could move them. And that's where the Ethernet cables go for the IP phone and everything.
Did you make any changes, like for a case about a network issue in the underground lab? Like any changes with ports in the last week?
I didn't change any ports. I did do a task which was like a network issue in the underground.
Because I'm trying to remember where I saw it, but I thought I saw somebody said they had tried swapping ports or whatnot, and that might have caused a problem. So we would want to try and hone those lines. Have you ever used a network toner before?
No, I haven't.
An analog toner? I'm trying to think of where it is. I think it's in the second drawer down in our office, behind Shane's desk. In the drawer called networking stuff, and then
Wave at me if you still need what's on the screen.
either the jack
Okay.
up there or the other end if we have a coupler, and then turn it on and we generate a signal, and you take the probe over to the patch panel in 235. Is anybody else?
Like an Ethernet tester.
To an extent, yes.
One of them has.
Okay, using the methods we just used before, change this to its other format, other notation for a derivative. And I want you to go ahead and try to find the general solution for this one. I'm going to give you a head start, and then I will also put it on the screen in a few minutes.
2 inch by maybe inch and a half thick box, and it's got a few cables that come off. One is like an RJ45, and one
like this?
Yes.
Okay. Well, I'll
We should have one. I think it's in the cabinet behind, actually, behind where Bryce sits in the afternoon, or behind where
yeah,
you
the
sit.
same one with like all the Ethernet cables and like the network adapters.
Yeah, I think it's in one of the top two drawers there.
Okay, I'll take a look.
Let's see, the 22nd.
Let's see, it's the K here. There we go. Now, in this one, you do want to go ahead and solve it for y equals blah, 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 blah. Because as often as you can, you do want that solution. The last one we couldn't because it was a y squared in our solution. And so algebraically, I've worked through that here with you. And notice that we have this plus c that comes out of our integral. And then I take that and I eventually say e to the c is just c. Because realistically, c just represents any constant. And if I have e to a constant, I just get another constant out of it. And so that's why I put these little subscripts on. I'm talking of, they're not the same constant, your different c's, but they just represent a constant. This equation right here is hugely significant. What is this equation? You should have seen it in about half a dozen places at least in the last 2 years. I mean, we've done it this year even. Now, this is the one where this is coming from that second chapter that I said we were going to do. I am skipping over a lot of their different specific models, but they all use the same equation. This represents radioactive decay. We're going to do one on Newton's law of cooling. This could be define population growth. Although typically, when you see it, you're going to say it's going to be especially of bacteria population, not necessarily people. APERT, yep, that's going to be your A equals P to the RT, which is going to be your compound interest. This is an equation that has so many different meanings, and I want to just step back to what did we just say. I want to remember
go into the port, and then the other one would plug in on the other end of the patch panel and would give you an indicator as to whether or not the cable that runs between is damaged at all.
Okay.
But in the absence of a analog toner or a digital toner, we can just go to U235A and look for the patch panel that's labeled for the corresponding P2003 and 2004 ports, and then follow the.
I didn't necessarily word that the best. I said this means the slope gets steeper as the function grows, although function, it's hard to tell, that's what I really wrote. What it means is
Confirm whether or not they are connected to
your slope is going to be determined entirely by what your function is. As you start out, you're going to be pretty flat, but the further you get away from your origin, the more you start to grow steeper and steeper and steeper and steeper and steeper and steeper. That y value itself, or remember the y value represents the function, that is going to represent how your slope grows, which it should make sense that if y equals ce to the kx,
they should be on dynamic.
your function
Okay.
That could be the problem with the
is very steep.
He's a pretty handy computer as well.
With large x's.
Okay.
This is probably the most popular differential equation that's out there. Meaning, of course, this one right here. It's going to be the most used. And like I promised you, we are going to finish out class today with a word problem. I looked through the different word problems, and this was the one that felt the most different for me. I don't think you've spent much time with Newton's law of cooling. And I'm going kind of fast here because I do want to give the people in the building a chance to put the computers away before we finish. So this is just stating what Newton's law of cooling is. Oh, I am going to modify this slightly because we're not going to compare it to x's. We're going to compare it to time. So I'm going to modify that variable. He probably is. It should be time to feed him again. All right, and I can tell you right here, we're not going to be able to finish because I'm going to let the students inside the building put their computers away. I am going to finish this problem for the recording, though, so you will want to take this or to watch the end of the recording. I am going to make a big deal out of the object's temperature changes as it's in the room, so it stays a variable. Whereas the room temperature is not going to be affected by our object. It's not going to be enough to heat the room up. So this one, the room temperature, is constant. So we go ahead and plug that constant in to the equation. And then K is just going to help us determine how quickly the temperature is going to change. And we are going to have to discover that equation. We'll give you a preview. So we can see down here, I'm going to set this as a dy over dt. I'm going to move my stuff to each side and integrate, solve it for y, and then play with the equation once I have the equation, which I will go through and do that on the video. So make sure you watch that last little section of what I record. All right, we had to stop this problem before class ended to get you guys out of class, but let's go ahead and finish it. Okay, so one of the things I kind of rushed through is I want to focus on the words that are in Newton's law of cooling and talk about how we translate that into math. So first of all, you see rate of change. By definition, that's a derivative. And we're taking the derivative with respect to time, which is why I'm using a t instead of an x. If you see the word proportional, or even is proportional, remember is your equal sign. Proportional means that you're going to multiply some constant times your object. In other words, you're not going to divide by the object. If it said inversely proportional or indirect, then you divide. We have the difference between the objects and the temperature of the surroundings. So difference indicates a subtraction. So you're going to take the temperature of object 1 and the temperature of object 2 and subtract them. So that's how I got this equation down here. It's just we take the words that indicate what Newton's law of cooling is, and we can very easily put that in an equation form. And of course, when I say easily, I do mean with practice. The more you practice, the more comfortable you'll be with that. And I'm not pretending that any high school student has had the practice to be super quick with that. But my goal is any AP calculus student is going to have more experience with it than the rest of the school. All right, so then that's where we get our equation from. And we go ahead and we plugged in the constant temperature. The room temperature is not changing when I bring this hot object into it. It's going to stay 60 degrees in the room. But our 100-degree object is going to change, so we're going to keep it as its variable. We are not going to plug in the 100% or the 100 until we are done with the problem. We have to do the math, do the calculus to it first. All right, so we have a couple issues. One of the issues is we don't know what this constant out in front is, this K value. And so we're going to have to go through a process which will involve solving for K and solving for some other things. But let's start playing with the situation. Oh, sorry, I just woke the baby. We'll pause for a moment and I'll be right back. Nope, he fell back asleep. All right. So what we're going to have here is we have dy dt equals k times y minus 60. We want to have our y's on the same side, so I'm going to multiply my time differential over to my other side. And I'm going to go ahead and I'm also going to divide by my term that has y. And because y is being subtracted, you are going to move the y minus 60 as a group over. It will be the easiest way to handle this. But let's see. And if we do it on one side, we do it on the other. So what we have now is 1 over y minus 60 dy equals k dt. And our next step is going to be, we're going to integrate both sides. If you do it on one side, you do it to the other. So on the first side, we have some u substitution. We're going to say u equals y minus 60, so your du is the same thing as dy. It's a good idea to check that just to make sure your du is going to not have another constant you're multiplying by that comes out of that situation. So we have here 1 over u du, and the integral of 1 over u du is the natural log of u. On the other side, we're taking the integral of k. All we have to do is put a t on there. But we do have one more thing, because it is an indefinite integral, so you do need to have your plus c. And again, it doesn't matter where you put your plus c. It doesn't make sense to put one on the y side and one on the t side. You don't have, because it's just two constants. So you add those together, subtract them, they're still just a constant. So we usually put it on the x side, or in this case, the t side, usually not the y side. So we have this equation, which I'm going to go ahead and plug back in what my u value equaled. That was equal to y minus 60. And you know what? Because I know, oops, that was way bigger than I thought, sorry. Because I know I'm going to be plugging numbers like 100, 90, 80 in there, I'm going to even just go ahead and use parentheses. I'm not going to worry about the absolute value, because I know later the numbers I'm plugging in won't accidentally give me a negative number inside the natural log. Okay, now you want to solve for y. Ultimately, you're trying to find what y equals anytime you're solving these. So you need to do the algebra so y is by itself. So we're going to use our trick about taking e to the natural log to break into the natural log. And if you do it on one side, you do it to the other. Here, our e and our natural log cancel, and we're left just with y minus 60 equals e to the kt, and then e to the c. It is a legal move, remember, to take what's in the exponent location. If you're adding them together, it's the same thing as giving each of those objects the same base. So e to the kt times e to the c. And very conveniently, e to the c is just another constant. So if I think of it as e to the c1, that's going to equal c2, which is, again, just a constant. It is a legal move to say that that's a constant and to put that out in front, like we did earlier. And we just have one step left. Just have to move 60 to the other side. So what we have here, this is called the general solution. But we need to find the particular solution so we can solve for what's happening in our scenario. So what we're going to do here is we want to solve for our k and we want to solve for our c. We need to look back at what the problem told us originally, and we can use that to solve for our variables. So, some helpful information here. And I know this is getting kind of busy with all my colors, sorry about that. But we know that initially our object was 100 degrees, And we know it cools 10 degrees in 10 minutes. So if I come down here and just write that down, the initial temp was 100 degrees and it cooled 10 degrees in 10 minutes. Those are both points on our graph. Those are our X and Y essentially. Because what happens here is this means at time equals 0 minutes, your temperature 1, which is our Y value, is going to be 100 degrees. And at time equals 10 minutes, your temperature is going to be 90 degrees. So we take that and we plug it in. We have, let's see, 100 is equal to, actually I'm going to change the color again just so it pops a little more. 100 is equal to the C value we don't know yet, times e to the K value we don't know yet, times the time of 0 minutes, plus 60. Conveniently, 0 times anything is still 0. And e to the 0 power is 1. So what I have here is 100 is equal to C times 1, which is just C, plus 60. Probably simplified a little more than you were necessarily expecting. So we get out our C value is equal to 40. Now, likewise, we can then take our equation and we're going to plug in our other data point, which is when the temperature was 90 degrees. And we're going to go ahead and use that C value now that we know it. We're going to take 40 times e to the K, which we still don't know, times 10 because we're looking at the 10-minute mark for the 90 degrees. And let's see, we've got 90 equals 40e 10k plus 60. I'm going to subtract 60 from both sides first. Divide by 40 because you can't break into the e value until we have that. And I believe I've got some stuff here to erase for my last class. Sorry about that. Thought I erased enough of the screen for you. All right, so then if I simplify that, I could say that's 3/4 equals e to the 10k. Now that e is by itself, it is a legal move to take the natural log so that your natural log of e will cancel and you get just what's in the power. Just so long as, if you do it on one side, you do it to the other. So we get the natural log of 3/4 is equal to 10k. And then we divide both sides by 10. And we get k is going to be the same thing as the natural log of 3/4 divided by 10. Or you could think of this as 1/10, the natural log of 3/4. Or you could think of this as the natural log of 3/4 to the 1/10 power. Doesn't really matter because ultimately you're going to put in a calculator anyway. I get that this is equal to negative 0.02877, blah, 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 blah. All right, so we found our equation now. So our particular solution for our situation is that y is going to equal 40e to the negative 0.02877 blah 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 t plus 60. That's our equation of the problem. And we're being asked earlier in the problem, way back up here, how much longer will it take the object to cool another 10 degrees. Now that we have the equation, we have the relationship established, we can use that to find how long it will take. So we know we want to go for 80 degrees because 90 degrees minus another 10 degrees would be 80 degrees. And we plug that in as our temperature of the object. And the T is what we're going to solve for. So solve this like an ogre. While the problem might feel more complicated as you go, the concept of solving it like an ogre never ends. You want to look for the thing that's on the outside layer, and pull that apart first. So moving that 60 is my first step. Now that 40 is the thing that's on the outside, so we're going to divide both sides by 40. And 20 divided by 40, I'm going to go ahead and simplify that to 1/2. And next I'm going to take the natural log of both sides because it's the only way to undo an exponential with the e. So we get out negative 0.02877 times t. Looks much more simple once we get rid of the exponential. And last but not least, we're going to divide by this decimal out here. And again, this is why calculators were invented. I get 24.09 minutes out of this. Now that does mean 24.09 minutes from the beginning, from when you brought it in. So if we're asking how much longer will it take the object to cool, remember it took 10 minutes to cool the first 10 degrees. And it's taking 24 minutes total to cool at this point 20 degrees. Ultimately, it's going to take 14 minutes more to cool to 80 degrees. So what this law of cooling says is you're going to cool the fastest at the beginning. So you went 10 degrees in 10 minutes, and then the next 10 degrees took another 14 minutes, and it's going to take even longer to cool another 10 degrees, and even longer than that to cool another 10 degrees, until you get yourself down to equilibrium of the 60 degrees in the room. So let me know if you have any questions. Remember, I do have office hours on Friday. That is not changing, even though we do have people back in the building. So I'm available. Just let me know if you have any questions. There are still some word problems I'm giving you that I haven't worked it out for that particular type of situation in front of you. But I'm happy to do that for you if you just let me know that you'd like to see that.